Yeah.
Okay, so we'll begin today. We basically went through sample prep, pre-processing, data processing, and then the next step in the CryoET workflow is analysis and annotation. And so we have a couple speakers from TFS, Tianbo, Zhai, and Mark McClendon, and they'll talk about AMIRA. What is your favorite part of the CryoET workflow?
Tianbo, you go first.
For me, that probably will be the annotation part of it, because nowadays there are like a array of different tools available for me to do a pretty accurate annotation. And I got to choose between either the manual one or some semi-automatic or even automatic annotation. So I find that really make the work a little bit easier in terms of the analysis. I would say that's probably my favorite part about it.
Excellent. And real quick introduction from myself. My name is Mark McClendon. I've been with our software group for about 3 years now. Previously, I used it during my graduate work. So I liked it so much, I went ahead and decided I wanted to do it professionally. So now I'm an account manager, and I'm going to leave my contact information in the chat, but we'll also be providing it in other ways. If you're interested in looking at AMIRA and how it can help you with your workflows, please send me a quick email, and we'll figure out, if it's the right software for you if you want to get it. And to your question, Ed, what's my favorite part in the CryoET workflow? It's definitely the part there's in deep learning, but specifically in the deep learning workflow, once you've done the annotation that Tianbo mentioned, you push a button and you train the model. And when you do that, it usually takes hours to create a good model, but that's my favorite part because you get to watch that in real time and see it graphically graphed out in terms of how well the model is doing. And you get to see it learn at each different epoch, each different step. And it's just, I don't know, something pleasurable about watching the computer do all this hard work, all this thinking, and getting smarter and smarter, represented by a graph going up and up and up. So that's definitely my favorite part.
Take it away.
Tianbo, I think they said take it away.
Oh, okay. Thank you. So with that being said, today's presentation will be focusing on the AMIRA software. It's one of those image platforms that I consider as a one-stop where you can transform your raw data into some of the meaningful statistics. And along the process, for today's presentation, I will be using a couple of cases to demonstrate how the annotation is done inside the software, how the analysis looks like, and of course, a general overview about the software in case you are not as familiar with AMIRA or even you are new to image analysis in general. So with that being said, the first number one takeaway, I hope, from my presentation, is that please consider AMIRA software as a standalone image analysis software. That means that the software doesn't need to be attached to a particular instrument, brand of instrument, and also it takes in a variety of images that coming from however many instruments that you may think of. So essentially, you may receive different formats of raw data, but there's a good chance that software can take in, load them, and start an analysis from there. And of course, it doesn't differentiate whether it's material science samples or it's life science samples. And also the software accepts a wide range of data size. There's a good chance, again, that even though the data could be very large, but it can still be processed inside the software. And also, one of the built-in of the software nowadays is there's an AI-assisted segmentation tool. Essentially, you can sort of bypass the heavy lifting part about image segmentation because as we go through the presentation, or maybe from couple sessions before, that you may have exposure to how the image analysis could be looked like, and the segmentation is normally considered as a one of those time-consuming and critical part. I will go to the workflow so that we can have a more vivid view about how segmentation looks like inside AMIRA. But again, to emphasize, when you try to initiate a image analysis, in this context, I think CryoET is one of those popular topics right now. And you could consider AMIRA as a standalone software where it's taking the raw images that you acquired, and it will process the image, essentially denoising, filtering, and it enables the initial 3D explorations. I think one of the strengths of the software is that it's taking 3D data set pretty well, so that we can have some sneak peek into the data set even before we start the official analysis of them. And then, as mentioned, segmentation will be followed, and segmentation is something that's going to be the critical part of it. And of course, many times people won't stop just at the segmentation. The quantification or be able to extract meaningful statistics is one of those end goals or deliverables for many of the projects. So this is also something available inside the software. So to put it in short, AMIRA provides you a one-stop image analysis platform where as soon as you acquire your raw data, you could start analysis. And the final deliverables many times are the statistic of your choice. Coming to the a little bit more into each of the key parts, I would start with the image processing. So the processing here, to be specific, will be more considered as like a pre-processing. As you might have experienced either after sample preparation or actual image analysis, you may notice the image quality of the raw data sometimes can be quite noisy. That's usually the one of the recommended first steps, is that to be able to denoise and to correct some of the artifacts as much as you can upstream in the analysis workflow. As you can imagine that even though you could still maybe able to get with rather noisy image down the workflow, but if you could upfront being able to pre-process your image to a level that is, number one, visually distinguishable. So for example, if you're trying to segment a particular biology structure, you definitely want to, at least visually, you can recognize, so that with the segmentation result, you know there's something you can compare to. You can confirm this is the structure that you're really looking at. So denoising can serve the purpose to give us a good starting point. But again, cannot overthink about pre-processing because again, there probably will be a certain limitation that you couldn't really denoise further. That will be okay because down the road, there's still additional methods, additional component of the workflow can support. But I would say image pre-processing, you can consider those as denoising or filtering as straightforward as these two. And also sometimes it's probably not as frequent, but if you do notice that the images that you required is misaligned, meaning slice to slice, you see a big discontinuity. You don't see the structure transition as smooth as you would expect. So there's a possibility because of their misalignment is happening there. So to be able to align the slices is also one of those important pre-processing steps. So after the pre-processing part, to be able to visualize is important in many ways, as sometimes, especially if the data set is very large, you do not necessarily able to present. It takes really long if you start analysis right away without being able to have a full understanding about the scope of your data set. And a lot of times I have seen for the cryo-EM images, it's a rather thin section. And then when the data set you received, probably it's a cube-looking 2D stack, but really the key information or the actual meaningful data only contains in that small central scene section. Then by being able to visually distinguish what is the useful data versus what is just the background early on, and then crop those away, trim out those unnecessary data set, can improve the speed of your later analysis quite dramatically. So again, in the software, you got the option to view the 2D slices, and you also got the option to understand how the 3D structure could looks like. But note, at this point, nothing has been done like physically to the data set. We're still just visually inspect them, and we may adjust the so-called color map to help us view a little bit better, but no actual physical change has been done to the data set. It is considered as either visualization, or you can say inspect your data before analysis. After these steps, here comes the critical part, and many times the most consuming part, is for virtually all the analysis, there will be certain defined region of interest. And those region of interest or structure of interest, they're usually buried along with other unrelated background or irrelevant structures. So being able to pinpoint and highlight those key structures proves to be very important. And nowadays, there are plenty of tools that everyone could use, and many of them are open source. Image analysis, the algorithm wide by itself is not like a secret or anything. It's a lot of those algorithms are based off open source algorithms. And so essentially you have so many different ways that you can achieve your segmentation goals. But to go down to the core of the segmentation is we're trying to classify the imaging data that we received pixel or voxel by voxel. So if we can find a good criteria, for example, every voxel has a different intensity value that embedded into it. If we can find a magic range where the structure of interest happen to fall under that intensity value range, then we can complete the classification task. Essentially, consider segmentation as every voxel going through every small component, every finite data set, going through a test, whether it belongs to the structure of interest or not. If you can set a good criteria, or if you can use a good tool or suitable tools to achieve this classification goals, then you would heading towards a better segmentation result. Because then you can later focus on only the region of interest to extract the statistic out of it. Without a reasonable segmentation, there's no way that we can extract any meaningful statistics. So this is a lot of emphasis onto the image analysis workflow in case you haven't done it. But for those of you who are familiar with, you would already know that segmentation is such an important and critical steps. Nowadays, again, with the booming of a lot of the deep learning related techniques, inside AMIRA, we have an AI assistant tool. But the concept of this, in case you haven't used any of them, is that we are essentially trying to provide learning material for the machine to understand the pattern of our structure of interest. So as the machine learn about those patterns that samples we provided, it will generate a so-called deep learning model. And then in turn, we will use that model in the hope that it can be generalized and applied to the entire data set and help us with the predictions. Because at this point, when we try to apply the model, after we teach the machine how to recognize the pattern, we extract that deep learning model and then we try to apply it. During that process, it's a educated guess from the machine side to tell us how we should classify individual pixels. Again, during the image analysis or segmentation in particular here, if you could try to view down to the pixel or voxel level, then you will find many of the algorithms or even the deep learning technique is making more sense probably, as essentially going back to the prediction part of the deep learning is that we got a model, we are able to extract such a model after we provide many of the small subset of our data set as a learning material to the machine. Then with the help of that particular model, when it is being applied back to the entire data set, it is going through almost like a voting process, and it's based on probabilities, which have a higher probability, then it will be classified as structure of interest. We probably will show inside the software and to further explain some of the application side of it. Again, this is just a visual impression. As you can imagine, to be able to segment a biology structure across a very crowded space could be quite challenging, but with carefully planned those training process, and here what you're seeing is the final prediction, and it's aligned quite well, and in particularly, if we're looking at this visual of all those identified subsecular structures. I'll try to play a short clip here. So those structures are being extracted from the 3D. Essentially, the identification process happens slice by slice, and then when they are put together, that's the 3D structure that we got to be identified. And inside that particular 3D structure, as here we're going to and view is some of those subcellular structures. And again, those segmentation really is a classifying all the pixels into different groups. And when those groups cluster together, you will see a certain structure of interest, and they are noted by different colors here. So as we went through the segmentation process, many methods can help us get to that structure of interest. I think by then, we're probably already halfway through. A lot of times, how to make best use of your segmented structure is another topic that people will spend time on. One of those key steps is definitely to be able to extract truthfully or extract the parameters of your interest, or even try to extract a parameter that is you have seen maybe from a publication. They may have a customized measurement trying to present, and you try to reproduce the result. And so those kind of like a quantification process, they are also available inside the software, and they are all enabled by a single module called a label analysis. Essentially, after the segmentation, what we get is a labeled image. So the image is being labeled for us, or in other words, are being classified for us, which pixel belongs to which class. And the next immediate steps is to be able to analyze those labeled structures. Inside the AMIRA software, there is a long list of available measures that you can choose from. And of course, you can customize those measures. But again, to be able to assemble and to be able to understand a particular measures in the context of AMIRA, you may need to read through some of the detailed descriptions under the user's guide. But many of the common measurements that you are familiar with are there. And in addition, there's some of the measurements that are more unique in the context of AMIRA. So I will be also showcasing one of those cases that we're seeing on the right-hand side, where membranes, the thickness of the membranes is being quantified. One of the other challenge, or sometimes I see during the research study, is that sometimes people would like to be able to make correlations, and draw some conclusions among two data sets. And sometimes those data sets may even come from different image modalities. So inside the software, this is in the context of AMIRA, it is called registration. Essentially, we're trying to register a primary image with some new images. They could be of different size, different modality, but they may share some of the fundamental key structures. And being able to register them, essentially align them so well that we can see the subtle difference, either by the size or by other parameters. This is of interest to many of the research. And this is something also available inside AMIRA. For this is the last slide for this first part of the description. Maybe there will be 2 more slides, but essentially here, if you are already an expert in terms of image analysis and you are getting new information and you try to test out new algorithms, this customized solution inside AMIRA is also available to you. So you can quickly try out some of the new algorithms that you learned. Those are a expanded function for expert users. To put in summary at this part of the session, consider AMIRA software as a standalone one-stop image analysis software. It helps you with the visualization, help you with the pre-processing, and definitely is a big help to classify the image to be able to finish a good segmentation job. And of course, many of the meaningful statistics, a long list of available measures that is also available for you to use. And as you can see, some of the strengths of the software license to be able to enhance the quality of the image and embedded this AI assist segmentation tool. And of course, a very comprehensive quantitative analysis. So before I go to some of the recorded videos and live demo, I would take some questions, if any, at this point. Okay. If no question at this point, we will move on.
Hold on one second. I think Ed's queuing up the questions.
No, I don't think we have too many, but since you have a lot of AI methods, how do you handle validation?
Validation, you mean the results from the segmentation? How do we validate whether that's making sense or not? Is that the question, please?
Correct.
Yeah. So the golden rule of validation is to compare your predicted results and overlay on top of the actual image and visually inspect whether they are correlating with the structure of interest. So I would always use that as a number one way to validate.
And just to add to what Tianbo said, like most traditional deep learning training, our program has a ratio where it initially splits the data you provide that's annotated into two data sets, the validation training set and then the training data set. So you'll be seeing a score as the data model is being trained, and the validation data set will never have been seen by that model. So you'll be seeing just how well it's going to do with data that it's never been exposed to. So that's another way that you might consider validation.
I have a question about also about the AI stuff. So it looks like you guys are using label data. Have you tried it all with any of like the recent unsupervised ones where you just kind of give it the image, let the model figure out what exists in the image and do the segmentation?
Sorry, I only hear the word label. Could you maybe someone help repeat through the mic, please? I'm a little bit didn't get the question part.
There's a speaker there.
Have you guys tried with any unsupervised methods where you just give it the image and let the model tease out what the different features are? Because I guess data annotation, especially for creating like good label data, it takes a non-trivial amount of time to do. Speaking from personal experience.
Sorry, you mentioned about unsupervised learning. Sorry, still a little bit missing some of the key content.
Yeah,
go ahead.
Yes, please.
Well, I was just gonna take that question because I think I caught the gist of it, and yeah, I've seen some examples of that in other softwares out there, the unsupervised, where basically you give it an image and you say, learn the features and segment what you think should come out of this. That's not something we've currently implemented in AMIRA. I know R&D is looking into it, but right now, all of our deep learning requires some amount of ground truth created by you. And it's kind of why we've done this, what I like to call the deep learning made easy button, where it requires very minimal ground truth. Because you're right, it can be time intensive if you want to create a good model. But we have this tool where you can essentially draw, and I'm not exaggerating here, for about 1 minute, and then train a model and predict and get a very large data set predicted on and segmented with only about 1 minute of annotation. Now, it's not going to be amazing. There's going to be an iterative step to get better and better, but it'll get you results within that time frame.
And then kind of adding on to that, do you guys have like the ability to pull together annotations from like multiple groups, or like if I've annotated one type of data and someone else annotated another one, and they're okay with like sharing that annotation with us so that it's like mutually beneficial, we train a model that's seen more types of data?
Tianbo, did you get that one?
So if the question is to whether we can transfer the annotated data from one person to the other, yes. Those are
Yeah, any type of like data sharing mechanism.
It doesn't necessarily as sophisticated like a sharing mechanism, but for the annotation part, essentially they are saved as the so-called label image. Every pixel is being classified 0, class 1, or 2, something like that. And those label image can be then transferred. It is pretty lightweight. It only contains the integer values. So those will become the so-called transferable annotated image. And then another person can open that and then continue with the annotation part.
And just to expand a little bit more, if you yourself had annotated data on your cryo images or whatever, and you had a colleague somewhere else on another campus that took their own data set, acquired it, and annotated it also, and you wanted to create a model that would try to predict well on both types of data sets. In AMIRA, you could combine both data sets and the annotation associated with them and train that model. So if that was your question, then yeah, it's pretty easy to just combine data sets and train a model that represents both of them. Not only that, but if you've already started and you've created a model on your own and it's doing a pretty good job, we have the ability to expand on that model, and it basically starts its learning deep learning model brain with the model you've already created, and then you can add new data and say, okay, learn this too into your current neural network with the associated weights.
Yeah, that answered my question. Thank you.
Thank you.
Continue.
Okay. So with that being said, some of the pre-recorded video to demonstrate maybe a case or two, and then I'm going to go inside the software so we can have a feel of how the annotation can be done and how the analysis workflow looks like. So first off, let me just present a short clip. And this is one of those typical cryo-EM data set, as you can see. But the key structures that people of interest here are those filament-looking structure across, spread out the entire 3D space. Inside the software, this is not necessarily an AI-assisted tool, but this is a more like a cylinder correlation tool that can help us to approximate to those with a cylindric template. We are able to try to match and segment those structures that look like a filament. So this is the interactive tool where we adjust what is the template should be look like, and how the diameter of the cylinder and how the length could be looks like, and then try to have everything else feature being figured out with one template that we provided. So specifically, after the correlation, that we are able to extract filament across all the 3D space, and also they share all different Porter angles. And as the color is trying to indicate it here, different angles is being assigned a different colors. Those more towards blue or even darker color are the so-called action wave that we're trying to identify. And this is one of those quantification parameters that available to use, is that after you segment the structure of interest, which is those cylindrical filament looking structures, and then we are able to take a measurement, because right now everything is being segmented as separated as possible, so that the measurement can be applied to individual filament looking structures. And when those measurement is performed, you will require you will get a value. For example, in this case, it's the Porter angles, and you can assign a color. Let's say for the higher angle, you want to have a color more towards blue, purple, or darker colors. And for the Porter angle that is small, you want to have a warmer color, so for like a red, yellow, orange. So this is how, after those kind of like color assignment has been happening, would be eventually give you some analysis and give you some insight in terms of where to find those structures that possess a parameter of interest. And going to the next, then of course, for all those parameters or measurements of interest, you can plot those histogram style statistics right away inside AMIRA, and you always get the option to export those in, for example, CSV format, and then you can post-process your data however you would like. It's just inside AMIRA, there are some options available for you to just extract everything inside the software. And another case that we had a brief mentioned about it, and I'll first explain the screenshot that you're currently seeing. So as we're trying to segment a membrane using the AI assisted tool, the concept of AI assist tool is that that was recorded in a previous version where we were using the so-called patch concept. So we will be placing small square across the different sizes across the 3D space, and then try to annotate where the structure should be and how the structure looks like. And once we assign those individual structures, we will then have the machine to generate a model in turn for the prediction part. Again, as mentioned, the prediction part is a educated guess using the deep learning model. And it went through every single imaging data. And then based on the probability, it will be classified the pixel as whether that's a structure of interest or not. So for those are classified as true to be a structure of interest, they are being highlighted in green. So slice by slice, and then eventually we're seeing a green 3D structure on the bottom part of the screen. And from there, once the segmentation is to satisfaction, then we're able to continue to process the data. In this particular case, the thickness is obtained through a computation module called thickness map. So it's trying to extract the thickness value across those individually segmented structure and then assign a color. When the color is more, as you see from the scale bar, as the color is more towards the red, it is more higher value. And then as it's towards purple or blue, they tend to represent a smaller value. So this is a video that I will fast forward, and then also along the process, if there are some key points, I will also pause. So this is about the case number 1 here. So this is the overview that I just explained inside of the software. And this is after the segmentation has been done. As you see, that the one way to be able to validate and trying to understand the quality of your segmentation visually is that you can overlay the 3D structure on top of what you already have, the raw image. In this case, because this could be a rather large data set, we're taking 3 slice view so that we're trying to save the computation time, but at the same time to understand the scope of our data set. As you can see, this is another view from that 3 cut plane on the X, Y, and Z. So the actual prediction part, the actual deep learning training part happens in a separate tab than what you have just seen. There's a dedicated tab called segmentation. We will perform such analysis. And as you see from different cut view, this is again a typical CryoEM data set. And the key structures, the most noticeable structures lies on the XY view. And as we get started, we want to understand the extent of the image, because as you can see from the other section view, the CryoEM dataset seems to lie in the middle part of the section, where the very top part or the bottom part of the dataset, even though they are acquired, they are not necessary. This is going back to the earlier question. Always try to trim down and narrow down to the region of your structure of interest. And going from here, there will be, again, some visualization check. And the actual AI assist segmentation starts when we create such a patch set. It is called a patch set, so it's essentially a set of small squares. We will rather randomly, but also try to have a good representation to place those across the 3D space. And then from there, we're going to annotate. Multiple ways to annotate those. I will show in the live demo. The brush is one of those most convenient way, of course. And then for every single small square or small patch, we want to make sure the structure of interest, if they exist inside, they're being properly annotated. So this is the subsample that the machine will receive. And after the machine receives the subsample, the training process will happen. And then the prediction will in turn provide again, it's an educated guess across all the 3D imaging data set. And we'll be seeing the full predicted membrane structure. So with that being said, I'll try to open a AMIRA 3D software and using yet another example for the final part of the presentation. The software itself is divided roughly into 2 parts, the operating window on the left and the display window on the right-hand side. As mentioned, for the annotation to get started, it happens inside the segmentation workroom. inside the segmentation workroom, there are a variety of tools that you can think of in terms of complete the annotation. I pick this brush tool as an example. So if you remember, the core of getting deep learning started at this point is that we can annotate some of the key structures, only part of it, of course. There are like 80 slices, but I probably would just pick one, maybe 3 slices across the 3D space, make some careful annotation. I will demonstrate the process. This is how I would annotate, for example. I will use one structure as an example. Let's say I want to machine to learn about this pattern and then try to predict all the tubular structure across the entire 3D space for this data set. So I will then assign this particular annotation as ROI, or structure of interest. And this is my sample. And of course, the plan is probably pick 2 or 3 slides across the 3D space and annotate those rather carefully. And this is only a simplified version. But then what we would do is we will create such a so-called region of interest set, ROI set. And you see the blue box. This is similar to the concept that you see from the video, the small patch. And then what we would do is essentially, once we are able to adjust this region of interest to a certain size, we want to make sure that everything inside this ROI set is being annotated. That means this is because the information contained inside this ROI set will be used for the prediction purpose. We'll add to it. So assume that you have done that for 2 or 3 slices, and you added maybe a couple of ROI sets. It could be of various size. It doesn't have to be a fixed size for the ROI. And then what we would do inside this AI-assist segmentation is that we will go to AI-assist segmentation, pick a model. The variety of model that is available, but for image segmentation, a lot of times the VG16 and 19 by itself has been proved robust, and we can take advantage of those models and start incrementally. Start with maybe just 10 epochs, and then we can turn on the tensor board to visually inspect as the training process is doing. And then we could launch the training. I probably wouldn't launch the training just because this is a so few sample, but to give you a sense of how the workflow could be looks like after a more carefully prepared annotation, more comprehensive ROI set, I will show you some of the expected results by using the exact same data set. So essentially how it could be looks like after you did more annotation, you place a few more ROI sets, and you perform incrementally from small epochs, and then increase from there. So this is, again, one of those expected results. So for the exact same image, instead of the patch concept, notice that we incorporate this ROI set and going towards the same annotation process. But as you can see, there are a little bit more patch size. And as you can imagine, for ROI set, we're also expecting definitely more than one across the 3D space. And the very initial impression is After we provide some of the samples to a limited location, then the machine, this is the first go around, it will help us try to pick up some of the similar features. As you can see, this initial run is very preliminary. Many of the complete structure is not got picked up. But the good news is that we now have a good starting point, as we do see that structure of interest, when they are being picked up, they tend to be the structure, part of the structure of interest. So with that bear in mind, we'll continue the similar process where we add a few more ROI sets, we annotate a few more, and we remove those belongs to be, turns to be false positive. And when the same process got repeated multiple rounds, we will be able to segment a variety of material of interest, not just the single tubular structure, but also many of the surrounding structures. They also can be captured along the process. But as mentioned, it's not a magic tool where you can, with a few click of button, then you get a perfect segmentation. It requires a careful planning, and it requires increment, understanding your result, and build upon what you already get. But the good news is, for many of the challenges, challenging segmentation inside CryoEM, that is turned to be very difficult by using traditional thresholds-based image segmentation tools. Deep learning open up a new, I would say, a new perspective, so that you can explore and you can grow your segmentation. Like previously, they may just be incomplete, and then as you put more information and as you build onto successful models, you are on the right track to eventually get a much more reasonable segmentation. It takes time, but again, the good news is once you get a reasonable model, it can be applied to similar data set, and it can be continue build upon what you already have. This is, I would say, some of the very attracting points about using AI-assisted segmentation. And I think this part of the takeaway is that inside AMIRA, we offer these options to you. Feel free to explore. Again, it requires a careful planning and a good annotation to be started off. But with that, with increment improvement, there's a very good chance, even for many of the challenging structures that we're trying to segment from a CryoEM dataset, they can be segmented in a very reasonable way. So with that being said, I will conclude my presentation here, and I think we have about 5 minutes left for any questions, please.
Thank you.
Thank you.
Questions?
I do have one question. It may be better directed to Mark, just because I know he's worked in auditory hair cells before. But I wanted to know if there was any part of the program that's detecting filaments that could actually detect branched filaments or determine the angle between filaments. Because in our system, we know not all the filaments are exactly kind of parallel or separate. We actually have a lot of them that branch. And we're interested in finding a way to quantify the angle of that branching.
Yeah, yeah. So it sounds like that might be one of my old colleagues. So yeah, good to talk to you. But yeah, if you're looking I'm glad Tianbo changed to this slide over here, because exactly what he was showing here could be applied to those filaments. If you're talking about the stereocilia themselves, they're a little bit more defined and easier to quantify if you can get a large view and segment all of them. If you're talking more about the intracellular structures, like maybe the actin filaments of them, that will be a little bit more challenging until you can make out the resolution of those filaments, because what we'll need to do is we'll need to actually segment individual filaments. So if you cannot make out with the resolution you're acquiring the individual filaments, you'll be hard pressed to quantify the directionality of those. But assuming you can, and maybe using the deep learning tools, you can not only trace each one of them using the deep learning segmentation, but then each one of them can be quantified for their angle of direction. And so, Tianbo, if you would change it to that color coded, or maybe it might be a in the middle of one of your videos. All of those colors right there, they can be exported to a CSV, you know, something that you could throw into Excel and graph out maybe a histogram of each one of the segments and their preferred orientation. And you can do that in relation to their spatial direction. So if you wanted to know, you know, maybe you think there's a special orientation or a preferred orientation near the top of that tomogram series compared to the bottom, you could also graph that out. So all the data is easily exported into, you know, your graphing software of choice. Even though you can graph in AMIRA, we know everyone has their preference in how they handle the data. Did that answer your question?
Kind of. I guess just one follow-up for clarification. So if you had like one single filament that had another filament branching off the side, would your program count those as two separate filaments in different directions? Or is there a way to distinguish that it's one filament that then splits into two?
One of the ways that we can do that would be with our, I believe it's called autoskeleton feature, where yeah, it counts that branch off as a new, I think they're called segments in our software. And so each of these segments will end at a node, and some of the segments share a node, which is a branching point. And so you can quantify, you know, how many branching points you have on a single structure or something like that. So depending on what you're looking for, if you know you have a lot of branching structures, you should probably use that autoskeleton type of analysis. But if you think you have individual fibers, then you can just segment them and quantify the individual segments as themselves.
Okay, awesome. Thank you.
I have a question about the like auto segmentation of tube functions. So I have a very large tube that I've been trying to use AMIRA to auto segment, and essentially it won't let in the dimensions of the tube. Is there a size restriction to how much, like how big the tube can be?
I hear the first part of the question that you have a large tube structures in your images.
Yes, and when I tried to like input the dimensions of the tube into AMIRA to like auto segment, it like wouldn't let them in. It said it was too big, and I was just wondering, does that mean there's like a size limitation to the tube segmentation feature?
Oh, size limitation for what segmentation feature?
Like the auto tube detection segmentation?
Were you referring to the cylindrical correlation at all, that module in particular, or?
Yes, yeah, that one.
Oh, okay. Size limitation, I would say that if you're worried that the tube is really big, that then the correlation template wouldn't allow that parameter, for example, the diameter of the cylinder to be input. I would say I didn't notice a specific limit on that, because essentially that you have two ways you can input. I don't know if you have used AMIRA, that's probably we can look into the actual case, but in AMIRA, as far as I know, that for the cylindrical template, you have two ways to input that template diameter. For example, you can just type the numbers, or you can visually drag the cylinder template to match the structure of your light. So in that sense, I don't see a set limit that will prevent you from further.
I will say that maybe a soft limit to using that cylinder correlation for the fiber tracing is the data size, because that is a pretty computationally intense algorithm. It's essentially going from point to point where it detects where it might be a fiber, and then it looks in a cone of directionality. And so that's a lot of computations just with each individual point. And, you have a huge data with, hundreds, thousands of voxels. So if you're having an issue, I'm wondering if you should maybe try doing a smaller set of your data. Just extract out a subvolume and see if you can accomplish your task there. Now, this is something that's meant for multiple different fibers being in your data structure. So if you just have one big fiber or one big cylinder,
Yeah.
oh, you do have, it's just one big cylinder.
Yeah.
Oh, okay. Then in that case, I don't think you would want to be using something like the cylinder correlation. You're just trying to segment that entire fiber, right? That singular one?
Yeah, there's like 2 layers to it, and I'm just trying to like segment the outer layer of it.
Ah, okay, okay. Yeah, have you just maybe we can talk offline a bit if you want to send a quick email, but I would suggest for something like that, it sounds like maybe a watershed feature might work, but I haven't seen your data, so it might be too noisy for that kind of approach. I'm sure there's something that you could do with deep learning too.
Okay, thank you. I might send you an email.
Okay. And we have some tutorials on our YouTube channel to use both of those deep learning and watershed features.
Thank you.
Okay.
Can we get both of their emails before they?
Yes, I have their emails. I'll forward them.
Okay.
So thank you.
Thank you.
Awesome. All right. Well, I know you guys are CryoTomo, but we will be in you guys' neck of the woods for the Tosca conference over at the Natural History Museum. So if you guys are interested in coming to our hands-on workshop, feel free to sign up at the Tosca conference. And yeah, we'll be there to see you and talk to you.
When is that?
That is in May. I think it's May 12th. I'm looking at my calendar right now. I think that will be May 12th. Yes. Okay. I was right.
Okay. See you soon.
All right. Thanks, guys.
Thank you.